Good morning again, everybody. And today we're going to continue our discussion of sequences. I want to briefly remind you some stuff we already know. So first of all, the definition of the limit. So an is a sequence, and we say that the limit of an is L. And what do I write here under the limit? N goes to infinity. There's nothing else I can write here. Whenever we're talking about a sequence, this is the only thing that makes sense. Okay? The limit is of an as n goes to infinity is L if for every epsilon there exists an n. N is the threshold index in our mind, the place for which, so such that if you went far enough in the sequence, if you've passed that big N, this implies that you're epsilon close to L. So this is the definition. We all agree that we're no longer terrified from it. We've been seeing these sorts of definitions already for a while, and we saw several examples. And the last, we didn't have that many theorems yet. So we saw a theorem that the limit, if it exists, it's unique. And we saw a theorem, and this we proved that if it has a limit, it's bounded. Very good. So if the limit of an exists, then an is a bounded sequence. And the terminology of a bounded sequence is exactly the same as the terminology of a bounded set. A sequence is bounded if it has an upper bound, capital M, and a lower bound, lowercase m. Or similarly, you can say if all the elements an in absolute value are less than or equal to some constant k. Right? That's the symmetric version, and we discussed that when we discussed boundedness of sets. Okay, so this is where we left off, and let's continue from here. So I want to first remark a couple of things. So remarks. One, this theorem is not an if and only if statement. So this is not an if and only if statement. So what do I mean by that? It is not true that if a sequence is bounded, it necessarily has a limit. Okay? Can you give me an example of a sequence, not a function? Okay? So when you throw out the word sine, we all see a picture in our heads, and we may know what you're talking about, but that's not a sequence. That's a function. And I know why you say, I guess I know why you said that, but we're talking about sequences. So can you think of a sequence which is bounded but does not have a limit? We already saw an example like that. Very good. So this would be a counter example. To prove that the other direction is false. This direction is false. So the sequence -1 to the power n. The sequence 1, -1, 1, -1, 1, -1. If I would plot it on the x-axis, it would look like this. 1, well, no, from your direction. 1, -1, 1, -1, 1, -1. Right? It doesn't have a limit. It doesn't converge to anything. You can go far out to infinity, and it will still rock back and forth from 1 to -1. Do you agree? But it's bounded. All the elements are between 1 and -1. Do you agree? Okay. And the second remark, so whenever you have a theorem, whenever you have any form of implication, then the converse is not necessarily true, but If a sequence is not bounded, then it does not have a limit. Do you agree to that? That's logic. Because if it were to have a limit, it would be bounded. Right? So if it's not bounded, it necessarily doesn't have a limit. Do you agree? Okay, so if an is not bounded, then it has no limit. Now there's a bit of a tricky issue here as far as terminology goes. So when we define the limit, we only defined finite limits. Okay, so here L is a finite number. There's also going to be a generalized version of this where we allow L to be infinity. We saw that for functions, but we're not there yet. Okay? So for now, when we say it has a limit, we mean a finite limit. Okay? And therefore, if it's not bounded by this theorem, it doesn't have a finite limit. It could have a limit infinity, but we didn't define that yet. So let's emphasize this here. Has no finite limit. Okay, is this clear? Yes?
When you say finite limit, that says n goes to infinity?
When I say finite limit, I mean that this is a finite number, not infinity. This always is the situation, n goes to infinity. There's no other thing that makes sense here. A sequence is a ordered set of numbers. The only limit concept that makes sense to discuss is when you go in the direction of the indices. Okay? I want to also say that, remember, last lecture on that board over there, we had some 10 or 12, I don't remember exactly, examples of sequences. Do you remember? And we discussed them intuitively. We proved like one or two. We proved, I think, that 1 over n goes to 0, right? And we proved that the constant sequence has a limit, which is that constant number. But we didn't prove many of them. And now we have a very easy way of proving that all those examples which were not bounded don't have a finite limit. Okay, so for example, that we had an arithmetic sequence. Remember? It's not bounded, right? It was getting bigger and bigger and bigger all the time, so it doesn't have a finite limit. It's easy to see. It's easy to agree with intuitively, but now we have a way of saying it and pinning it down as a proof. Okay? So for example, we had the last example, which was a recursive sequence. Remember? It had a recursive formula, and we saw that the numbers get bigger and bigger. Not bounded, therefore doesn't have a finite limit. And all those unbounded examples. Yes?
Let's say, for example, 1 over n minus 1 as equals to an.
1 over?
N minus 1.
Okay.
So when n equals 1, that doesn't exist.
Right. So if you want to give a sequence, okay, that's not directly related to any of this, but if you want to give a sequence 1 over n minus 1, then that can be defined only for n being greater than or equal to 2. And that's fine. A sequence doesn't necessarily have to start with an element a1, okay? Because remember we said you can always drop finitely many elements, or throw in more elements, or change elements. As long as you're tampering only with finitely many of them, you're not changing, you're changing the sequence, but you're not changing the limit phenomenon. Okay? Okay, so that's this theorem and these remarks. And the next thing I want to discuss is more theorems, and the next one is the limit arithmetics. So theorem. Question? Yes?
But we say, like, if an is bounded, there is a limit, but if it's bounded at infinity...
What do you mean by bounded at infinity?
I mean, not bounded.
I'm not sure I understand what you're saying. You're saying bounded at infinity. The notion of bounded is not a notion a pointwise notion, to say that a sequence is bounded means that there is an upper bound, a number such that all the elements are less than or equal to that upper bound. It's not bounded at infinity or bounded at 5. It's bounded from above and from below. So what do you mean in order for me to understand?
It's not bounded, right?
Okay, so the concept of the sequence going to infinity is something we did not define yet, so please postpone your question until we define it. Okay, so far we only defined finite limits for sequences. Okay? Okay, theorem. Assume that we have two sequences, an which goes to L as n goes to infinity, and bn which goes to k as n goes to infinity. And again, I'm emphasizing, L and k are numbers. That's the only thing we defined yet so far. Okay. Then, and this is going to look very similar to the limit arithmetics theorem that we had for functions. So 1, for any constant c in R, c times an goes to c times L. Bless you. Do you agree? Okay. 2, an plus bn, if you add the sequences element-wise, and you check what happens at the limit, what's going to happen? What's the limit going to be? L plus k. If you multiply the sequences, what's the limit going to be? Right? And finally, if you take the quotient, then the limit is going to be L over k. But here we have to add a disclaimer. This only makes sense. We can only discuss this situation when k is not 0 and when the bn's are not 0.
When n goes to what?
Right.
Infinity.
Okay, that's a good question, but it's also an opportunity to state it again. When you're talking about sequences, if you happen to forget to write, like I didn't do it on purpose, but if you happen to forget writing under the arrow what is the limit you're discussing, for sequences, it's still well defined. The only thing that can happen for sequences is n going to infinity. There's no other sort of limit process for sequences. Does that make sense? Do you see why nothing else would make sense? What does it mean n goes to 5? Right? Do you agree? Question, yes. So again, what does it mean n going to 1? Okay, a sequence is a set, an ordered set of elements. There's A1, A2, A3. What does it mean that n goes to 1? Okay, A1 is a fixed element. Okay, what does it mean that the indices go to 1? What kind of process would you imagine? That you start with 17 and then do 17, 16, 15, 14 and go down to 1? Okay, that's not a... It's kind of... Do you agree that it's not a meaningful thing to discuss for sequences? For functions, it is. Okay, but for sequences, do you agree? So for sequences, we're only discussing what happens when the indices go to infinity. Okay, that's the only thing that makes sense. Okay.
But we don't have a problem on 4?
In 4? Why?
To be no.
No, we ruled out
Right.
the dangerous traps of dividing by 0. Okay? So example, we can't do that many because we haven't proved that many, but even something very basic, if you look at the sequence 1 plus 1 over n, what's the limit of this sequence as n goes to infinity? So we proved that 1 over n goes to 0, right? Do you agree?
Yeah.
1 is a constant sequence. We proved that constant sequence go to that constant, right? So by theorem number 2, when we add them, what is the limit going to be? 1 plus 0, which is 1. Do you agree?
Yeah.
Okay. So before I write another well, nothing here is too challenging, but another a bit more sophisticated example, let me add a couple more rules, which are also theorems, in this flavor. So, if for any n, a n is greater than or equal to 0, then the root of a n, which makes sense because we required all of them to be non-negative, converges to what? Okay, I'm still under the assumption that a n goes to L. Maybe I'll add it here. Assume a n goes to L. Okay, then what would the root of a n converge to? Right, the square root of L. So this will be is what? Then, yeah. Oh, sorry. Let me rewrite this and allow it to have. So first of all, you were very correct that I forgot an n here. So here's theorem, and let's call this 1. And then 2, the absolute value of a n. And now I'm not requiring this assumption that they're all non-negative. What would this converge to? Right, the absolute value of L. As with, maybe let's remark this. Okay, so maybe, okay, let's put a 3 here, and then we'll add a remark. If, or let's write it like this, a n converges to 0 if and only if a n in absolute value converges to 0. So if this L happens to be 0, then property number 2 becomes an if and only if statement. And then the remark is that in general, if L is not 0, then the converse to number 2 is false. So 2 said, okay, you know that a n goes to L, then a n in absolute value goes to L in absolute value. The converse would be if a n in absolute value goes to L, goes to L in absolute value, implies a n goes to L. This would be the converse to number 2, and the remark claims that this is false. This is not a theorem. Can you think of a counterexample? Can you think of a sequence that if I take its absolute value, it has a limit, and call that the absolute value of L. But if I throw the absolute value, suddenly things go wrong.
-1 to the n.
Right. The same counterexample that worked a bit earlier, very good, will work here. So counterexample. Good. -1 to the n. Negative 1 to the n, negative 1, 1, negative 1, 1, negative 1, 1, etc., does not have a limit, right? But if you put it in absolute value, what do you get? What is the absolute value of this sequence? It's the constant sequence 1. It has a limit, 1. But without the absolute value, it doesn't have a limit. Do you agree that this is a counterexample? Everybody?
Yeah.
Okay, good. Okay, let's do some more examples using the limit arithmetics. So I forgot to write here, limit arithmetics. Let's add that. Limit arithmetics. So let's do an example using all these limit arithmetics properties together with some of these properties with these other little statements. So here's another example. So suppose I want to look at the limit as n goes to infinity. Just as with functions, I'm going back and forth between the notations of limit n goes to infinity and the notation of just writing the algebraic expression and putting an arrow, n goes to infinity. Both are perfectly fine. Okay? So suppose I want to look at the sequence n plus 1 divided by 3n minus 2 over n, all of this to the power 1/2. So what would the limit be? So what would the first step of my calculation be? How do you tackle things like this?
The 1/2 stays because of the theorem 1.
Okay, so we'll the point. Okay, so maybe this is a good place to remark the following. We can't do things. We can work algebraically on this as much as we want, but the going to the limit, the taking n to infinity, has to happen at once. Okay, at one time. You can't do it in steps. You can't take some of the n's to infinity, leave the others, and then take more n's to infinity and leave the others. And you can't do it in steps. We'll see it. I'll show you an example maybe a bit later of how that can get you very, very wrong things. Okay? So if I wrote still limit here, it means that whatever I write here has to equal to this expression algebraically. I'm not taking n's to infinity yet. Okay? What do you mean by remove the square root?
You know that the limit of a square root is equal to if the theorem number...
So once I find the limit of what sits inside, I will be able to write that the limit of the whole thing is the root of the limit of this. But I don't know this limit yet. So what, for example, would you want me to write here? I can't write just the limit of this. That would not be true. Right? So... right, divide top and bottom by n. We've seen that. It's the same idea as with functions, right? So I would write here, dividing the top by n, I would get 1 plus 1 over n. And dividing the bottom by n, I would get 3 minus 2 over n squared. And all this to the power 1/2. Do you agree that this is the same? I did not go to the limit yet. Okay, equals... Now what? Let me rewrite it one more time. I'm doing this with extreme detail, but just for this example. So the top I'm going to leave untouched. The bottom I'm going to write 3 minus 2 times 1 over n times 1 over n. And then I'm going to write this 1/2 here. Okay? Now I can use all these theorems. As n goes to infinity, 1 over n goes to 0. By limit arithmetics, 1 plus 1 over n goes to 1. So this goes to 1. 1 over n goes to 0. So the product of two sequences that go to 0 also go to 0. Right? 2 times that, all this is a sequence, it was this sequence, also goes to 0, because it's the product of 3 sequences. This goes to 0, this goes to 0, this goes to 2. So the difference here goes to 3. So the quotient here, none of these are 0. The limit is 3. So this goes to 1, this goes to 3. So the quotient goes to 1/3. And therefore, now I can use the theorem about the roots. So this goes to 1/3, everything in the parentheses. So the root of that goes to the root of 1/3, which can be written as 1/√3. So everything I did here, I'm guessing that you would know how to do this without thinking all those details in your head, just kind of doing it. You know the rules. They're easy, but that's what's hiding there. That's the formal theory that allows us to do that. Okay? It's these theorems. And if we were to do this course with full rigor, we would have to prove all these theorems that I just wrote using the definition of the limit. Okay? We did 1 or 2 examples in functions. I think we proved that the limit of the sum is the sum of the limits. It would be similar for here, and I'm not going to do all these proofs using the definition, not in this course. Okay? Is this clear? Is everybody good with this? Okay? I'm assuming you can already do things like this on your own easily, and you're going to have more practice on the homework. Okay. So the statement at this point is, when we want to calculate limits, usually we don't resort to the definition, but we use these kinds of theorems and some more, and let's write down some more. And the some more that I'm gonna write are not gonna surprise you either. They're also theorems that we've met in the context of limits of functions. So here are some more theorems about limits. It is very, very important. I mean, I'm going to say it now. I said it before. I'm going to say it again. So in Hebrew we say I'm a bit of a nudnik, but it's important to do a lot of practice. Okay, so the theoretic layer in this course has its place. It appears mostly in the lectures when we build up the theory. But for you, it's very, very important to be able to master these techniques, to be able to do calculations. And you should be able to do these things very, very easily without struggling with them. And the only way to get to that point is to do tons of them. Okay? Not look at me do a calculation and understand it. That never gets you anywhere. You have to do 15,000 calculations of limits, then you know I know how to calculate limits. There's no way you can surprise me, and we can move on. And you have to do that for limits of functions and for limits of sequences, and later for finding points of continuity and discontinuity, and for calculating derivatives, and for calculating integrals, and so on and so forth. A lot of work in this course. Okay? Oh, you look so... I'm sorry. I mean, it's morning, it's raining outside, and don't look gloomy. Smile. Good. Okay. No, but seriously, it's important to practice these things. It's really important to practice them. Okay. So here are a couple more theorems. So all the theorems we had so far were kind of required that we're discussing a sequence that has a limit. Okay? And these theorems kind of tell us what to do when we don't know how to directly calculate the limit. So for example, if an is going to have a limit, an has a limit, and bn is not necessarily going to have a limit, but it's going to be bounded, and bn is bounded, Oh, sorry. This theorem, we want the limit of an to be 0. Then, what's the theorem? You know this from functions. Right. Then an times bn also has a limit, and that limit is 0. Okay? So this is a situation which we want, which is useful. Maybe let's just do an example right away. So for example, suppose I consider the sequence 1 over n times sine of n. This is a sequence, an. No, let's not call it an. Let's just leave it like that. Do you recognize this is a product of two sequences? Do you agree that this one goes to 0? We know that. Do you agree? What about this sequence, sine of n? Think about it a second. Does it have a limit? Well, how do you know that it doesn't? I mean, I would think that when you first encounter it, it's not obvious if it does have a limit or not, right? Because as n gets bigger and bigger, and that's the only thing that we're discussing, right? N goes to infinity. This sequence is kind of lives on the sine wave, and we're only looking at the values at integers. Do you agree? Sine of 1, sine of 2, sine of 3, sine of 4. We don't know those values. Do you agree? We usually only discuss sines for various multiples of pi. Pi, 2 pi, pi over 2, pi over 4. What is sine of 15? It's not completely obvious, right? So it's not clear if this thing does converge or not. Maybe good intuition is that since it sits on the sine wave, it doesn't. But it's not completely clear. Okay? So in any case, since we don't know that it converges, we cannot use limit arithmetics. Right? But what can we say about sine of n? It's bounded. Whatever n is, sine of 795, I don't know exactly what that is, but it's between -1 and 1 because the function only takes values between -1 and 1. Do you agree? So this is bounded. This is bounded. And therefore, by this theorem, we have a product of a sequence that goes to 0 times a bounded sequence. Therefore, the product goes to 0. Okay? Even though we cannot use limit arithmetics here. Clear? Yes?
We don't care about what sine n is because 1 over n is 0, so whatever it is.
Right. The only reason I was trying to discuss this sequence is just to get you to stimulate some discussion about specifically this sequence. What I'm using here is this theorem, and in this theorem, I don't care about whether this has a limit or not. I only care that it's bounded. It satisfies the conditions of the theorem. I can conclude that the product goes to 0. Done. Okay? Okay. So here's another theorem. So the next one you also know. It's going to be the sandwich theorem. Not many surprises so far. Everything is very similar to limits of functions. And if you've been studying those well, and if you're familiar with those, and if you feel comfortable with those, then this is not a big deal. So here's the next one, the sandwich theorem. So help me phrase it. You should be able to do that. What do I want to write? No, 0 is no longer a necessity here. Right, I have 3 sequences. How are you going to call them?
G.
No, G is a function. You have to let go of functions. Let go. Sequences. How are you going to call them?
A, B, and
AN, BN, and CN. Okay, good. So assume, and what do they satisfy? Right. So assume AN is less than or equal to BN is less than or equal to CN. Right? And what else do we need to require? Right, that the limits of the outer ones coincide. So the limit of AN is L, and this L is also the limit of CN. And what is the result? Then, right, then the limit of BN is also L. Does everybody agree? I want to observe something, and in fact this is relevant to other theorems. I could have remarked that earlier. In order for this to hold, in order for this statement to be true, this is a statement about limits, about something that happens down the indices, or up the indices. Okay? I only need to require this to hold, not for any n, but for some n and onwards. If this goes wrong for some reason, for the first 5 million elements, it's not going to change what happens at the limit. Okay? So, what I would add is assume that for some, or maybe for n greater than n, this holds. So starting at some index, suddenly they start obeying this relation. Okay? Even if at the beginning, and the beginning can be very big, they didn't obey this, it doesn't matter. If starting at some index, they started obeying this, then the limit phenomena, and that's what this theorem is about, don't mind what happened at the beginning. We can add that at the previous theorem too. So here, if the limit of AN is 0, and Bn is bounded, that's okay, so there's no real place to add it here. So maybe this is the first place where it makes sense. Okay, good. Okay, so let's do an example. So example. Maybe let's do a couple of examples. So let's look at this example. 1 over n times sine n. We did similar things for functions, very similar. So this is the exact same example we did a minute ago with bounded times a sequence that goes to 0. Let's do it with sandwich. So I'm going to rewrite it. As sine n over n. Do you agree? And I want to somehow bound this sequence between two other sequences, which I know their limits. So what would you do here? What is the natural thing to do? Right. Sine n is between -1 and 1. So sine n over n is between 1 over n and -1 over n. Do you agree to this? Everybody? And now we can sandwich it. 1 over n goes to 0 as n goes to infinity. That we know. What about -1 over n? Also, why? Convince me.
Because that number 2, or number 3.
Because 1 over n.
Okay, okay, I didn't think of that, but that's also true. In absolute value, it goes to 0. So by a previous theorem, it goes to 0 without the absolute value as well. That's true. Another way of saying it is this is a scalar, -1, times the sequence 1 over n. 1 over n goes to 0, so -1 times 1 over n goes to -1 times 0. Blame it arithmetics. Okay, so both ways are good. And what's the conclusion? That what lies in between goes to 0 by sandwich. Big C. Sandwich. Clear? Questions? Okay. So let's do a more interesting example. Less trivial. Again for the sandwich theorem. So here's another example. Suppose that an is the sequence n factorial divided by n to the power n. First of all, does everybody know what factorial is? What this exclamation mark in the means? Okay, this just means that I'm taking n times n minus 1 times n minus 2 times n minus 3 all the way down to times 3 times 2 times 1. Does everybody know that? Okay. So, this is no longer intuitive. It's not obvious, at least not for starters, right? Maybe if you think about it a bit okay, so let's think about it a bit. How do we decipher a sequence? How do we get intuition? What can we do? Right. Let's start to just find out what this sequence is. Okay, so let's do that. So intuition. This is not the calculation. Intuition. Did I spell this right?
Yeah.
Okay. Intuition. I'm going to start finding out what the elements are to get a feeling for it. Sometimes that works. Sometimes it doesn't. So for n equals 1, that's the first element. It's 1 factorial, which is 1, divided by 1 to the power 1. It's just 1. Right? What about 2? 2 factorial is 2 times 1. It's 2, divided by 2 squared. So 2 divided by 4, it's 1/2. Let me know if I'm losing anybody. Okay? You should be able to follow this. Nothing tricky. What's 3 factorial? It's 6, divided by 3 to the power 3. That's 27. So what's 6 over 27? I can cancel out a 3 in both. So it's what? 2 over 9. Do you agree? Okay. Do I want to do one more? Let's do one more. Okay. 4 factorial divided by 4 to the power 4. Okay, so before I even do the factorial and the 4 to the power 4, I'm going to cancel one of the 4's. So it's the same as 3 factorial divided by 4 to the power 3. Do you agree? Yep. So 3 factorial is 6. 4 to the power 3 is 4 times 4, that's 16, times 4 is 64. So it's 6 over 64. I can still divide it by 2. So it's 3 over 32. Do you agree? Okay. Are you getting a feeling for this? Is it starting to communicate? Maybe you need some more, but I think what's going on is starting to become evident. Okay? So for example, what you should be able to see is that this sequence is dominated by the sequence 1 over n. Okay, so that's, it seems to me, okay, 1 over n is the sequence 1, 1/2, 1/3, 1/4. This is our sequence, and this is 1 over n. Do you agree that you kind of see that for all elements, they're less than or equal. Do you see that? And it gets more obvious if you write more elements. So here they start out with equality. Then 1/3 is 3/9, so it's bigger. 1/4 is already 8/32. It's even bigger. If you write one more, you get even more convinced. Do you agree? Okay. So this is the intuition that I want to formalize. Okay, I want to claim. Okay, so claim n factorial over n to the power n is less than or equal to 1/n. That's what the intuition suggests. It's not a proof. This is not a proof. This is just, because maybe it goes wrong for the 700th element. Maybe. Not reasonable, but maybe. If I want to prove that it doesn't, I somehow have to prove this statement. Okay? So how do I prove a statement like this? Any suggestions?
I don't know if this would count as like an actual proof, but I mean, like when I'm just thinking about it, n factorial is going to be, if you take something like 5, 4, 3, 2, 1, but n to the n is 5, 5, 5, 5, 5. So you have like 5/5 times 4/5 times 3/5. All of that's going to be times 1/5. So 1/5 times 1 times a fraction is going to be less than 1.
Right. I agree to that perfectly. In order to make it a proof, you can make it a proof, but in order to make it a proof, you have to say it for n's, not for 5. Okay? Okay, so let me repeat that in case it was not clear. The statement is n factorial is, I'm going to say it for n, not for 5, is n times n minus 1, n minus 2, n minus 3, and so on. Whereas n to the power n is n times n times n times n times n times n, right? N times. So this is going to be significantly bigger than this, right? Because here I'm multiplying elements that are getting smaller and smaller, and here they're fixed. Okay? And I can even throw out the first 1/n in this, and it will still be very, very small, whereas this is just 1/n. Okay? So let me formalize that. Let me formalize that. So proof. By the way, another way of proving something like this, I'm not going to do it. I'm going to do it the way you suggested. But another way of doing it is by induction. Do you know what induction is? Okay? So that's another way of doing it. And whenever you have claims about sequences, not limit claims, but claims that hold for every n, you can prove them using the induction. Okay, so proof. Let me rewrite this. This holds if and only if. IFF is another way of saying if and only if. Okay? If and only if. And I'm going to cross multiply. N factorial times n is less than or equal to n to the power n. Do you agree that this statement and this statement are identical? Yes? Okay. And this holds if and only if. Now I can cancel out one of the n's. So n factorial is less than or equal to n to the power n minus 1. Do you agree? And this holds if and only if. And now I'm going to do exactly what you suggested. I'm just going to open it up and see what happens there. N times n minus 1 times n minus 2 dot 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 3, 2, 1 is less than or equal to n times n times n times n times dot 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 times n. Right? And how many elements do we have here? Well, how many elements do we have on the left side? N of them. So there are n folks here. N. And how many elements do we have on the right side? No, not n, n minus 1. So there are n minus 1 here. Do you agree? And, well, one of the elements here that I'm multiplying by is just 1. Right? Do you agree that I can cross this one out, because multiplying by 1 is like doing nothing? So I can cross this out, and now I have n minus 1 elements on this side as well. Do you agree to that? The 1. It ends with times 1. Doing times 1 is like doing nothing. So I crossed it out, and now I have n minus 1 factors in this product. And I have n minus 1 factors in this product. And each and every one of the factors on the right side is bigger than the factor on the left side. So, of course, the product is going to be bigger. Do you agree? So this, which is true.
The original question is the limit, right?
Yeah, we're only, so all of this is proving this claim. Okay, so in a minute I'm going to say how we continue from this claim. Well, you can guess, but let's first agree that this is, okay, maybe, okay, so I tried to flow with writing it, but maybe a more formal way of writing it would say, okay, this is true, therefore this is true, therefore this is true, therefore this is true. Okay, writing it backwards would be. Do you agree to this proof?
I don't understand why on the right side it's n minus 1 numbers.
Here?
Yeah.
Because it was this, n factorial, and here it was n to the power n minus 1. Okay? Okay, so how do we wrap this up now? So all we said, all we proved so far is this fact. Okay? And the way we proved it was formal, but the way we got to it was following our intuition. Okay? And the intuition was obtained from just writing down the elements and kind of letting them speak to us. So what do we conclude? What can we say now? Remember, what we're looking for is the limit. Very good. So now we can say that the sequence we're discussing, n factorial over n to the power n, is less than or equal to 1 over n. We just proved that. And as you said, it's greater than or equal to 0. Why? Because everything here is just n's. So it's always positive, right? And now what? Final touch?
Sandwich.
Yay. This goes to 0 as n goes to infinity. This goes to 0. It's the constant sequence 0 as n goes to infinity. Therefore, this thing in the middle goes to 0 as n goes to infinity by sandwich. Questions? Okay. So this is already an example that's a bit more or less trivial. Maybe let's take our break now and continue with more of the discussion of sequences afterwards.